Let's try some specific heat problems from the class calorimetry problems handout. So here are the equations given to you. You will need only these 4 equations to solve all the questions on this handout. So let's try a few together. The solutions to these are posted on the class Brightspace website, so you can look there as well. Let's start with a simple question. How much heat is lost by 40 grams of ice when it cools from negative 5 degrees Celsius to positive 15 degrees to negative 15 degrees Celsius? So in all problems like this, the first thing to do is to figure out what is given and what is required. So I'm given the mass of ice as 40 grams. It's not given in the question, but hopefully I have some way of knowing the specific heat capacity of ice as 2.5 joules per grams per degree Celsius. I'm given the initial temperature and the final temperature, -5 and -15 degrees Celsius respectively. And they're asking me how much heat is lost. So the required is Q. So I go to my list of formulas and say which one can I use. I have mass, I have specific heat capacity, I am being asked for Q. Do I have delta T? Well, I have initial and final, which tells me that the change in temperature would be final minus initial, -15 minus -5 gives me -10. So I do have delta T. So all I need to do is sub these values into the equation. So then Q equals, the mass is 40 grams. If you want, you can write the units at each point or not and just write the final units. I'm okay with both. Only when you do factor label, you have to write units with every numerical value. The change in temperature, -10, and the specific heat capacity. So let's do our dimensional analysis and figure out what the units would be. Like I said, you don't have to do it. You can just simply write the units at the end. Let's bring out a calculator and figure out that this is a -1000 joules. So you could also write this as 1 kilojoules of energy is released. So that's what the negative is saying. So the negative tells me this is exothermic energy is released or, as was mentioned, lost in the question. Let's try one more problem. What mass of water at 10 degrees Celsius would be required to cool this mass of water, which is at 100 degrees Celsius, to a final temperature of 35 degrees Celsius? So the answer given to us is 11.7. Let's see if we get that same answer or not. So let's organize the information that is given to us in a way that can make sense. So it looks like there is 2 different water temperatures. So there is cold water and then there is hot water. So let's write the information we know about both of these. So they're asking us what mass at 10 degrees. So that means the mass of cold water is not known to us, but we know that the temperature of the cold water is 10 degrees Celsius. The mass of the hot water is given as 4.5 kilograms. I'm just going to write that as times 10 to the 3 grams. The temperature of the hot water is given to us as 100 degrees Celsius, and you are mixing these 2 waters together so that the final temperature is 35 degrees Celsius. So again, let's look at our equations and see how can I solve for this. So these are my 4 equations. Let me try to see which one of these should I be using. So right away I see that there is temperature change, there is mass. So looks like this is a very good candidate. And it is also obvious to me that someone is gaining energy and someone is losing energy. So looks like this might be another useful equation. So let's start here. Let's first figure out who is gaining and who is losing energy. So if you mix hot and cold water, the hot water is the one that would be losing energy. So let's use this equation. Cold water would gain and hot water would lose energy. So let's plug this equation for both cold and hot water. So it's a mass of cold water times delta T of cold water. So this is initial temperature, final temperature is the same for both. So the delta T for cold water would be 35 minus 10, 25 degrees Celsius, and the delta T for hot water would be 35 final minus initial, so negative 65 degrees Celsius. I don't know the mass of cold water, I leave that as it is. So we would say mass cold water, delta T cold water, specific heat capacity of cold water is equal to negative Q lost, so mass hot water, delta T hot water, C hot water. So then let's look at what is given and what is the unknown. So the mass of cold water is the unknown. Do I know the change in temperature for cold water? Yes. The specific heat capacity of water would be the same, 4.18. So yes, I know that. Do I know the mass of hot water? Yes, 4.5 into 10 to the 3. The change in temperature for hot water and the specific heat capacity is going to be the same. Hopefully you see that if you have the same specific heat capacity on both sides, you can pretty much ignore that. Now, the unknown is the mass of cold water. So let's rewrite this equation to isolate the mass of cold water. So I get mass of hot water times change in temperature for hot water divided by the change in temperature for cold water. I have all of these values up here. Let me plug them in to get the mass of cold water needed would be negative 4.5 into 10 to the 3 grams times the temperature change is negative 65 degrees Celsius over the temperature change here is 25 degrees Celsius. So my solution ends up being 11.7 into 10 to the 3 grams or 11.7 kilograms. This is the mass of cold water needed.